It is. All right, happy Thursday. We're Thursday week 5. So we are so close to halfway. Next week, after our Tuesday, we'll be sorry. Next week after Tuesday's meeting, we'll be halfway through the term. So we are almost there. We are more than halfway through the material. Once we finish section 6, we're more than halfway through the material or unit 6, chapter 6, whatever. So this is going to be a good night. I really love binomial probability. I know it is a place where we struggle a little bit, but hopefully I can get you there. Hopefully I can get you to understanding. So um, section 6.2, we're building off of section 6.1. So we're going to talk about what a binomial experiment is. And then we're going to figure out the probabilities of binomial experiments. We'll be using your fancy little calculator. We'll be using that to calculate the binomial probabilities because it would be a lot of work doing it by hand. So we definitely are going to do it with the calculator. You learn a fancy calculator function. And then we're also going to compute the mean and the standard deviation of our binomial random variable. And the graphing part is, I don't even remember if there really is graphing at the end. If it is, it's just a baby part, and you're just going to look at it and say, oh, that's cool, and then move on. So it's slightly longer than Tuesdays, but it's still not a super long section. So let's just jump right in. I'm happy you're all here. Okay, so these are the things that are required for a binomial experiment. We we must have a fixed number of trials. Every time we repeat the experiment, it would be a trial. So, for example, on Tuesday we were talking about shooting free throws. So, um, every time that you step up to shoot free throws, it would be a new trial. So every single time, so if I'm drawing cards from a deck of cards, every new card that I draw would be a new trial. The trials have to be independent. So this kind of throws out some of the other stuff that we did, but the trials need to be independent. The outcome of one trial can't affect the outcome of the other trials. And also, for every trial, there needs to be two mutually exclusive or disjoint outcomes. So it doesn't mean that there's only two choices. It just basically is like success or failure. So for every trial, we need to have a success and a failure. So when we were talking about like rolling dice, if a 3 is a success, there are 5 other numbers that are a failure. So we have a success or a failure. So a success would be a 3, failure would be all the other numbers. So, and the probability of success has to be fixed for every trial. So every time you do a trial, you have to have the same probability of getting a success. So this is the requirement for a binomial experiment. And um, we're going to look at what is and what isn't. We're going to look at some examples. But when I ask you to do a binomial probability, you're just going to be like, okay, this is a binomial experiment. I don't believe any of the questions ask you to decide if it is. I know the test does not test you on, is this a binomial probability experiment or isn't? I'm not testing you on that. I just want you to see for your own purposes how to use this. And I'm going to give you an example of where I've used it in real life. And caught a student cheating at the high school. But I'm going to give you an example that I've used it in real life. All right, so let's move on. Okay, so this notation is important. So n is going to be the number of trials. So lowercase n, it is the number of trials. P is going to be the probability of success. So the probability of failure then would be the complement of that. Probability of success, we're going to use our little italicized p. So our x is the binomial random variable, the capital X is kind of like we did in 6.1, we have the capital X, whereas a lowercase x is the number of trials. Don't worry, it's not going to be hard to, you're not going to get stuck confusing them because, I mean, they look almost the same, but the lowercase x is what we use for number of successes we're looking for. It'll become clearer later. So we're going to determine whether or not something is a binomial experiment. So here's our first example. A player rolls a pair of fair die 10 times. The number X of sevens rolled is recorded. All right. So first thing we need to know is it a fixed number of trials? Yeah, fixed number of trials. Are there two mutually exclusive options? So we have a failure or a success. So rolling a 7 is a success. Rolling anything else is a failure. So yes. Oh, so it's 2 die, but rolling 7 is success. Anything else is failure. So there's two mutually exclusive outcomes. So is the probability the same every time? Yeah, the same probability of rolling a 7 every single time. So this is a binomial experiment. It is. This is a good one. All right, let's look at the next one. The 11 largest airlines had an on-time percentage of 84.7% in November 2001, according to the Air Travel Consumer Report. So we're trying to figure out the reasons for delays. An official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that need to be selected is recorded. So think about what we need. So the probability of success, 84.7%. That's good. Is there every single trial, does it have the same probability of success? Yeah. Two possible outcomes. It's either delayed or it's not delayed. That's good. Here in the next one is where the problem is. Fixed number of trials. It does not have a fixed number of trials because she's going to keep selecting flights until she gets 10 that are not on time. So we don't know how many trials they're going to do. It's not a fixed number of trials, therefore, not a binomial experiment. It's not a fixed number of trials. All right, let's do another one. I think we have one more. Yep, this is it. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. This is a tricky one. So first, let's talk fixed number of trials. Yes, randomly selects 4 students. There's my trials. Then we have, are there 2 possible outcomes, success and failure? Yes, so success is choosing a female. Failure would be choosing a male or non-binary or anything that is not female. All right. The next one is where we have an issue, the probability of success. So you would think, it seems like, there's 55% chance of getting a female. However, take one student out of the classroom. Let's say that I take one student out of the classroom and it's a female. Now, instead of 55% female, the number of female or the percent that are female is going to be different because I removed one. Or let's say the first one was a male. If the first one I took out is a male, now there's larger than a 55% females left in the class. So they're all coming out of the same pool. So the probability is going to change as I'm removing students. If that makes sense. So this is not binomial because the trials are not independent. So the probability of success changes once I take somebody out of the room. Any questions on these before we move on? All right. Okay, so the next pieces are not things that you're going to need for any questions or anything. It's just kind of the buildup to binomial probability and why it's a really good idea to use a calculator function rather than the math that we've been doing. But I'm going to show you how crazy things can get, actually. We're going to do a tree diagram. So according to the Red Cross, 7% of the people in the United States have blood type O negative. So we take a simple random sample of size 4, and the number of people with the blood type O negative is recorded. So we're going to create a diagram, and it's going to be crazy. We're going to use a tree diagram. So in my first trial, so this is all the trials. This is wild, and I'm going to walk you through it. In my first trial, I can either get a success or failure. So I have that right here. I either got a success or failure. So if I got a success on the first trial, I can either get success or failure coming off that one for the second trial. Same thing, if I got a failure on the first trial, I can either get success or failure on the second trial. So then we go to the third trial, and each of the options, so I could have gotten all 4 successes right there, or I could have had 2 successes and a failure and then another success. So these are all ways of doing this. Kind of like, remember when we were way back in chapter 5, we rolled 2 dice, and 4 was a different configuration than 4-3. They're 2 different outcomes. So there's one way that I can get 4 successes. So I only have one way to get 4 successes. So number of successes, 4, there's one way to get 4. So how many ways to get 3? There's 1, 2, 3, 4 ways to get 3 successes. Let's take a look at 2 successes. So 2 successes, there's 1, 2, 3, 4, 5, 6 ways to get 2 successes. Let's take 1 success. There's 1, 2, 3, 4. There's 4 ways to get 1 success. And finally, there's 1 way to get 0 successes. So this is a lot. Could you imagine if we did 6 trials? Can you imagine how wild this would get? Or 8 trials or 10 trials? Trust me, it's really ugly and really gigantic, and you don't want to see it. Trust me. It's wild. So I'm going to show you what math we would need to do to find those probabilities. So remember, we take the outcome times the probabilities. So we're looking at, this is and, remember and probabilities, we multiply them all together. You guys remember and probabilities? So if I am getting 4 successes, so we have 1 success times the second success and a second success and a third success and a fourth success. So that's 0.93 multiplied by itself 4 times to figure out the probability of getting, sorry, I just lied. That's failure. 1 failure and 2, it's same thing, just flip it. Failure and failure and failure and failure. So we have a 74.8% chance of getting 4 failures. So when we look at the probability of getting 1 success, so that's 3 failures, which is right here, times 1 success. So that's 1 failure and another failure and another failure and 1 success. But there's 4 ways to do this. So I multiply it by 4 because there's 4 ways to get just 1 success. So once again, that's 22.5% or probability. Yeah, probability 22.5%. So getting 2 successes, there's 6 different ways to get 2 successes. So I to the second power times to the second power, and then we multiply it by 6, and then we have that probability. And then we keep doing that. Now, this is my probability distribution, but think about how cumbersome this would be, because what if you had to figure out how many successes we had with 8 trials? That would not be fun. It wouldn't be fun at all. And there's some combinatorics you can do to get there, but still, it is not a whole lot of fun. It is a lot of math. That's why we have a calculator function. So this is my probability distribution right here, but it's a lot of work. Therefore, we have a We have a function, a calculator function that can get us there. All right. So with the combinatorics, this is the formula right here that we use if we wanted to do it basically by hand. So yes, you can do this in your calculator. You absolutely can. And it's a little more work than using the binomial function. This right here, down here, this is what we're going to be using. We are not going to be using this top one that I just circled. We're not going to be using this. We're going to be using what I just highlighted in yellow because it is super easy in your calculator. And that's what we're going to do. And I will show you how to use that. If you really love combinatorics, you really love combinations and permutations, you can message me and I'll walk you through it, but we're not going to do that. It's a little more complicated, and I would rather try to keep it simple. Rather not confuse you on something that already kind of confuses people. So here's what this is. Binomial PDF, well, we use this when we're looking for an exact number of successes. So if I was looking for the probability of getting exactly 2 people out of 4 with blood type O negative, I would use binomial PDF. This right here, N, is number of trials. This is probability of success. And this is number of successes you're looking for. I'll give you a second to mark yours down. All right. All right. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. Probability of success. In a random sample of 20 car-owning households, number of trials, we want to know the probability exactly 5 have 3 or more cars. So when we are dealing with exactly, when we are being precise, exactly, we're going to use the function binom PDF. Think that the P doesn't stand for precise, but mnemonic device, think of it as precise. Our number of trials, we have 20 car owning households. Probability of success is 35%, so change it to a decimal. And we're looking for the number of successes we want is 5. So we're looking for the probability exactly 5 have 3 or more cars. So think of what the tree diagram would look like with 20 trials. We don't have that much paper. I don't have room on my iPad for that. That would be really crazy. So I'm going to pop over to my calculator. Pop over to the calculator to get to the binomial. So binom PDF stands for binomial probability distributions. If you look above, so hold on, this right here, this button, it says DISTR. This is distributions. So we're looking at a binomial probability distribution. So we want to go into the distribution menu. So you're going to hit second vars, and it'll get you to this screen right here. So second vars. Now some calculators have it a different letter or a different number. So we're just going to scroll down till we get to binom PDF. On my calculator, it's letter A. So we're going to binom PDF. So once again, I'm going to get out of here. Second, vars. Vars is underneath our circle arrow thing here. To scroll down to binom PDF and then hit enter. If you don't have this screen, then you're going to enter it like this. You're going to enter it with the numbers with the comma in between. I have this screen, so my number of trials is 20. The probability is 0.35. They're in the same order as you'd put them if you don't have this screen. And the number of successes is 5. So we have 20 trials, 35% chance of randomly choosing a car owning household with that has 3 or more cars. We're looking for 5, probability of choosing 5 out of 20. And hit enter. So this is what it looks like. This is how you would enter it if you don't have that screen. So 20, comma, 0.35, comma 5.
I have a question.
Yes.
Mine, when I'm doing the second vars, I go down to the binomial PDF like you did.
Mhm.
And when I click enter, it's taking me to the second var stats with the X and Y list.
Okay, I've never heard that before. Are you starting from this screen, this screen? Are you starting from the main screen? Because if you're starting from something else, it's going to take you weird places. So make sure you're in the
Mm,
home screen when you start.
okay, if it has me in the second var stats right now, how do I get back to my home
So do
screen?
second mode and it'll get you out of there.
Second mode. Where okay. Oh,
Okay, all right.
perfect.
Okay, then you should be able to do second vars and scroll all the way down to the binom PDF, and then you should be good.
Perfect. Thank you.
You're welcome. I'm glad I could help. All right, hit enter, and I have my probability that the value of X is exactly 5 is equal to, I'm going to do 0.1272. Okay. Did we all get there? Did our calculators all work after the little hiccup? Okay, good, 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 good. Because yay. Okay, we're gonna step it up now. We're gonna change just a little bit, step it up the difficulty. Well, not really difficulty, but just learn something new. I love new stuff. And that's why you guys are here, because you like to learn new stuff. Or you want a degree and a good job that makes more money, one or the other, but learning new stuff is fun. All right. This was if I was using the combinatorics, so I'm going to show you where this is. You don't have to use it, but every once in a while I get a student that's super interested. So I'm just going to show you where it is in the calculator. And so if I hit the math button and go over to prob, which is over here, it's the third option. And what you put first is number of trials. Choose 5 of them. And then it wants to know what percent it is for success. So 0.35. And then you what, 5 successes, which means that 1 minus the probability for failure, I'm going to have 15 failures. That's basically what you're calculating. So you take your 20 trials, choose 5 of them, and then 35%, 5 successes, and 15, 1 minus 35%, 15 successes. You should get the same answer. It's doing that math. Yeah, it is the exact same thing. It does the same math. I just prefer the binom PDF because you don't have to remember as many things. Using the combinatorics like this, you have to remember a lot more things. There's a lot more things like, where does this go? What do I put there? I'm only going to show you it once. I'm never going to use it again, but I know some of the tutors in the tutoring center occasionally will go to this because it's fun. And I know that a lot of the videos, because I know a lot of people in class go to YouTube, so it is a valid way to do it, but a lot of YouTubers will do this method. So I want you to know it's valid and everything, but I only ever use binom. I just am showing it once and I'm going to back off, and you can forget it ever existed if you'd like, which I'm going to do that right now. Bam. Okay. I'm on this page now. We're going to forget it ever existed. Okay. So now this we're looking for a random sample of 20 car owning households. We're still at the 20. We want to know the probability that less than four have three or more cars. Less than four. So that means four is not included. We're looking at three or two or one or zero. So four is not included. So probability that X is less than four is the same thing as the probability that X is less than or equal to three. This is the money right here. This is what we're looking for. We have a different function when we're doing less than or equal to. We're going to use binom CDF. This literally does stand for cumulative. The C stands for cumulative. Cumulative just means add them all up until you get to a certain point. So it is cumulative. That's why I said think of the P on the other one, even though it doesn't mean precise, think of it as precise because that might stick in your head which one to use. P for precise, C for cumulative. So we will still do 20 trials. Probability of success is 35%. And then three or fewer successes. So 20, 0.35, three or fewer successes. So we're going to jump back to the other screen. I'm going to get rid of that right there. I'm going to clear this out because I don't even want to look at it. So we're going to go back to our distribution menu, second vars, and just scroll down. It's right under the PDF. CDF is right under it. So that's the one we want because it's cumulative. It's not precise, it's cumulative. So our number of trials is 20. Probability is 0.35. My X value, successes is three or fewer. So if you don't have that menu, it would look like this. And I'm going to hit enter. So about almost 4.5% chance of getting three or fewer out of 20 trials. Were we able to get there? Okay, good. Good, good, good. Just got to make sure. I don't want to leave anybody behind. That's always my biggest fear. I don't like leaving people behind. Okay. So now I'm going to do the one that makes everybody mad, but I'm going to try to break it down. I'm going to try to make it visual so you can get an idea of what's happening. That's the same thing. Okay, we're going to go there. So if you were doing it some other way, you're going to need to find the precise of each of them and then add them together, but we don't want to do that. We're going to stick with our binom CDF. All right. Now, now we still have the same 35%. We still have our random sample of 20 car owning households. At least four is what we're looking for. We're looking for at least four. Oh, good. I'm glad you like the P for precise and C for cumulative. That's how I remembered it when I was in school. So that's why I stick with that. That's why I tell it you guys, because if there's something that helped me remember it, it might help somebody else. If you don't like it, you can toss it out, but I really like the precise and cumulative. That's the way I keep them straight in my head. So we're looking for at least. So I'm not going to put all of the numbers from 1 through 20, but I'm going to do a few. So 0, 1, 2, 3, 4, 5, 6, 7, ... So we're looking for the probability that our variable is greater than or equal to 4. At least is the same thing as greater than or equal to. So what we're looking for is the probability that we are somewhere in there. That's what we're looking for, somewhere in there. So the probability we're greater than or equal to 4 is the same thing as the probability that x is not less than or equal to 3. So this is what it is not. It's not those. So every time we see the words at least, we use the complement rule. I'm going to say it again. Every time we hear the words at least, we use the complement rule. Therefore, what we're going to do, 1 minus the probability that x is less than or equal to 3. This will get us there because what this is going to do is it's going to find us this and then subtract it from 1. That's what we're going to do. There's a couple of different ways that we can do this, and I'm going to show you both of them in your calculator. And a lot of it has to do with how brave are you with your calculator. So first, it's going to be 1 minus binom CDF because it's cumulative. We're going to use the 20, 0.353. All right. I'm going to pretend we didn't already do the 20, the 3 or fewer. I'm going to start from scratch because I don't want to jump in halfway and lose somebody. So I'm going to jump over here. We're just going to erase it. We're going to start fresh. Okay. Once again, I'm going to go into second vars, go all the way down to binom, CDF, or 20 trials, 0.35 and 3. It should already be in your calculator. If it's not, then you're going to need to enter it like this again. And I have that now. So now that I have this, I can do 1 minus. You notice that above your little negative sign right here, it says ANS. That means answer. That will paste the previous answer. So if I do second negative sign, it just pastes that answer in there. And I do 1 minus the answer. And I get the 95.56%. I'll show you the other way to do this. 1 second here, 0.9556. Okay. If you like, if you are brave, even if you're not brave, if you just want to do it this way, you can put the 1 minus in first and then go to your second vars. Go all the way down and do your 20 trials, 0.35 and 3. And then it just pastes it in there. It just pastes it afterwards, so you can do all the math at once. I'm going to show you one more magical thing that not everybody has this ability, but some of you do. And for those of you that have this ability, I want you to see how cool it is and be able to use it. So I put the 1 minus in. So I'm going to arrow up and I'm going to highlight the binom CDF 20.353 and I'm going to hit enter. It'll paste it for me. Not all the calculators can do this. Unfortunately, the 83 can't. I think about half of the 84s can, but it's really good. It's also good if I had a typo. Let's pretend that I was meant to put 4 in here, which I didn't. So I could paste it in and then change it. Like if I made a typo, because you know me, queen of typos, and then I could paste it and use it. So if you have that ability, copy paste is your friend. If you don't worry about it. I'll pretend it's really not that cool. It's really not that cool at all. Okay. Questions before I move on? It's a sad thing. I can play with the calculator all day. I won't, but I could. All right. So if you see at least, use the complement rule. Be very careful choosing this value. That value should be the first value not included in your set. So the first value not included in your successes. So if I'm looking for greater than or equal to 4, 3 is the first one not included. So that's what that number should be. I'll write it down. First not included value. Because one of the most common errors is people will do this, but they'll put a 4 there instead of a 3. So it's the first not included value. All right, you guys ready? I want you to try these. Do as many as you can do with what we just did. Now, letter D, I haven't showed you how to do that. You can either attempt it or you can just leave it and wait until we go over it. So I'm going to give you a couple of minutes. I would like you to try those. I'm going to work quietly behind you, so if you get stuck, you can look up. I'm not going to do D yet, though, because we're going to go over that together. Give y'all a moment because I'm fast. Only because I do this frequently. All right. How'd we do? I'm leaving D alone. If you tried it, that's fantastic. I'm gonna leave it alone for a second. Any questions on the first 3? Did anybody not get it correct and not know why? You got C wrong? Did you put 3 instead of 2? Yeah. So it's at least 3. So 3 is probably 3 is part of the included values. So it's the first not included value that you need to put there. You rounded and probably shouldn't have. I just go out 4 decimal places because usually I round my percents to 2 decimal places. So I didn't tell you where to round to, so you're good. You weren't brave enough to try 3 or try D. I know D is a little bit weird, but I put it in there. I don't know if there's any problems in the homework like that or not. And I'm pretty darn sure the test isn't going to have something like that, but it's really nice to understand what's happening. So let's take a look at D. I'm gonna once again put the numbers down. I'm gonna write them out. So 0, 1, 2, 3, 4, 6, 7. I'm gonna go to 10. Okay. What I'm looking for between 5 and 7 inclusive. That means 5 and 7 are included in it. So I want this number of successes. So what I don't want 4 or fewer. So I don't want those. And I don't want 8, 9, or 10. I don't want those. So what I can do, I can figure out, let me see here, this probability of 7 or fewer. I can figure out 7 or fewer. Then I can subtract off the 4 or fewer. So this is what it'll look like in your calculator. So it'll be binom CDF 20 0.417. So that gives me 7654321 minus binom CDF 20 0.414. That gives me, I'm subtracting off the 0, 1, 2, 3, 4. So I'm going to flip over to my calculator. I'll give you a second to write it down. Then I'm going to flip over to my calculator and show you. I'll give you a minute. Make sure you can write it down first. All right. So I'm going to go binom, once again, CDF, 20 trials, 0.41. We're going to do 7. We'll see. Okay, enter. Now I'm just going to put a subtraction right there and go back in. See how we do. And I'm going to do 20, but I want to do 4 because I'm subtracting off 4 or fewer. Okay, and hit enter. Yeah, good job. Good job. Yep. So that's how you can get that range in the middle. This is really, all of this is really just something that's going to take practice. All of the, like A through C is what you're really going to be practicing. I think there might be one homework question that does the middle range. I can't remember. It's really funny is that um, I actually, the beginning of the week when I'm setting up the week's materials on Sundays, or sometimes I set them up Saturday and then do it, but I actually look at the homework assignments. I look through them. But I do so much math all week long because I teach 6 different subjects at the high school and then I teach here. So I forget pretty much everything that I've set up and I looked at it. I mean, I know how to do it, but I don't remember what the assignments look like. There's just too much.
I'm sorry, did you say 6 subjects at the high school?
I do. Yes.
That must be rough.
I teach geometry, algebra 2, AP pre-calculus, AP calculus AB, and AP calculus BC.
Oh my gosh.
Oh, I teach physics. I teach physics. There's still 6. So somehow I don't know. Sometimes my math was weird. I teach physics also. I have one section of physics. Yeah. I'm a glutton
Wow.
for punishment. It's a small high school and that's kind of what happens. I love it though. I
Yeah,
would
of
get
course.
bored.
Hmm, love that.
Like if I was
I
just like
have
teaching algebra 1 all day, I'd be bored.
I have a question.
Yes.
Can you remind me on number C what determines when we do the 1 minus binomial CDF versus just doing the binomial CDF?
These 2 little words right here.
The at least.
Yes.
Okay, thank you.
Yes. Because at least 3 means 3 or more. So it's 3 or more, therefore, but I don't have a greater than function. That was a great question, by the way. I don't have a greater than function, so I have to use the less than or equal to so that and then do the 1 minus to subtract it off. So this is the first not included value. So if it's 3 or more, at least 3 or more, then it's not 2 or fewer.
Thank you.
You're welcome. I'm glad you asked that. Okay. I love that. I love that, Shiloh. See, you guys who are watching the video, you're missing out on all the cool chatter in the chat. I read the things that are important to the class, but I I there's cool chatter that happens. That's awesome, Shiloh. That's awesome. I love it. Physics is hard. Physics is definitely hard. All right. We're gonna move on. So, I know that you've already had so many different ways to calculate mean and standard deviation. Now, I'm going to tell you, these are not the last ones. You're going to get a couple more. But today, this is what we're doing. Our mean, and its mean, its expected value, the number that we would expect to get. So basically, if I did 100 trials and the probability of getting a success was 40%, I would expect 40 out of those 100 to be successes. That's what we're calculating with the mean. It's really that simple. The standard deviation is a little more difficult. It is the number of trials times the probability of success times the probability of failure, and we take the square root of that. That gives us the standard deviation. Now, the standard deviation is going to have the same meaning it always does. You're going to still use it to determine if something is an outlier, something's unusual. So one of the ways that we figure out if it's unusual is if it occurs less than 5% of the time. So if my probability back here is less than 5%, like this one right here, so if it's less than 5%, then it is considered unusual. So we still are going to keep that rule of thumb, but we also have the standard deviation. The two standard deviation rule still applies. So you can choose which method you want to use to find the outliers, but I believe your homework's going to ask you to find that mean and standard deviation. They may call it mean or they may call it expected value, but either way, it's the same thing. The N is the number of trials, P is the probability of success. So we're going to do a little bit of that. We're already on 24 of 29 on our slides. We're almost done. All right. According to the Experian Automotive Service, automotive, 35% of all car owning households have 3 or more cars. We took a simple random sample of 400 car owning households. We're going to find the mean and the standard deviation. All right. So for the mean, my mu sub x is the number of trials. So that's 400 times the probability of success. Make sure to turn it into a decimal. You just math it out. So I would expect out of 400, there would be 140 households that have 3 or more cars. That's what my expected value is. All right. Standard deviation is going to help us to determine um, within what range it would be okay, where things would still be usual values, where we wouldn't think something is unusual. It's going to help us to determine that range. So thinking about when we find the standard deviation, think about like applying the empirical rule to it and looking at what's in the 95% area. All right. So I'm going to take my mu sub or my sigma sub x, take the number of trials times the probability of success times the probability of failure. Yes, if you want to, you can just put 0.65 into your calculator. But every time I've written 0.65 instead of 1 minus 0.35, people ask me where 0.65 comes from. So I'm going to write it like this. So then you just put it in your calculators, math it out. You should be able to put it in there all at once. You may need to be really careful with your parentheses. Be real careful with the parentheses, but you should be able to just put it in all at once. If you're not comfortable doing that, that's okay. Feel free to just do what's under the radical first and then take the square root of it. That's fine. But I got 9.54. Questions about those calculations yet? Okay. So now, this little thing that I'm going to give you is something that's going to come up over and over again. It's going to come up in the next several chapters. Actually, I think it comes up in every chapter from here on out. So, as the okay, as the number of trials increases, our probability distribution gets more and more bell-shaped. It is going to be more and more normal or bell-shaped as we increase our trials. Quite possibly in one of the quizzes, you're going to be asked about this. You're going to be asked what happens as the number of trials increases, or it might say what causes this to be bell-shaped. I don't remember the exact question, but our binomial probability distribution, it becomes bell-shaped as the number of trials gets bigger. It is bell-shaped if the number of trials times the number of successes times the number of failures is greater than or equal to 10. This determines whether or not your distribution is normal. There needs to be a significant number of successes and failures within your population or your sample. So this right here, so if it says, is this always true? So as the number of trials increases, will it always be bell-shaped? Say yes, as long as NP times 1 minus P is greater than or equal to 10. So yes, it will be bell-shaped if that is true. This is going to keep coming up. We're going to be using it to determine if things are bell-shaped. It's determine if things are normal. That's the other word for it. Is it normal? You test for normality by determining if it's bell-shaped by this, the NP times 1 minus P greater than or equal to 10. Now, let me tell you, at the very beginning of this term, I said, hey, make sure you're not using Google or AI because our book uses a different test than you're going to get on Google. It's very, very similar, but it's a little bit different. Our book used a little bit different one, and I grade based on this because this is what's in our book and this is what I'm teaching. So Google and AI and a lot of videos use something slightly different, but this is what we're going to be using. NP times 1 minus P greater than or equal to 10. It's not a huge difference, but it's a little bit different. All right. So this just determines if it's bell-shaped. So write that down, star it, highlight it, something so that you know that it exists. So you can jump back to it. Maybe put a tab on it because we're going to keep jumping back to it. Okay. So in order to determine if something is an outlier, we're going to be using the empirical rule. If it says in our bell-shaped distribution, 95% of all of our observations are within 2 standard deviations of the mean. So if it is outside that interval, it's considered unusual. If the observations occur less than 5% of the time, it is considered unusual. We've been talking about this already, so just remember, keep that in your noggin because it doesn't go away. All right, let's do an example. We already know this. This is what we've already got this, that we had our 140 for our mean and 9.54 for our standard deviation. So what happened We conduct a simple random sample of 400 car-owning households. We found that 162 had 3 or more cars. We want to know if it's unusual. So what we're going to do is we're going to determine, so there's a couple of different ways we can do this. You can look at the z-score, or you can just find the bounds, find the 2 standard deviation bounds. So remember, a z-score would be x minus mu divided by standard deviation. So I'm going to do this both ways. You choose what you like. So I'm going to do this both ways. First, I'm going to find the z-score. Let's use pink. Pink is pretty. So my x would be the 162 minus 140 divided by 9.54. Remember, if you put this whole thing in your calculator at once, that you need to put parentheses around the numerator. So let's do this. I got a z-score 2.31 approximately. That makes it an outlier. That makes it unusual. I'm gonna do it the other way. Let's do green. So I'm gonna do 140 plus, no, that's not 140. 140 plus 2 times 9.54. Now I'm gonna put that in my calculator. That's not a 9. Equals 159.08. Therefore, any value higher than 159.08 would be an outlier. So yes, it is unusual. Yes, it's unusual. Questions on this? The next screen, you're going to be doing one on your own. All right. We're going to look back at the wireless only households. Was it 35% or 41%? I hate that that's not on there. Keep telling myself I'm going to fix that. 41%. Okay. 41%. All right. In a simple random sample of 300 households, 143 were wireless only. Is it unusual? I would like you to find the mean and the standard deviation and then choose whichever method you would like to determine if it would be unusual. So I'm going to give you a minute, then I will slowly work behind you. How'd we do? Yes, it is unusual. Good. Yeah, you are right. That is unusual. Do we all get unusual? We feeling groovy? Yay! Love it. Love it. All right, so we're still on recording. I love this. Yay! All the right answers in the comments. I love this. So, we're still on recording. So, do we have any questions that for the good of the group? Any questions while on recording? Okay, I'm going to turn off the recording now.